We're now going to look at some basics of the SAR signal. Firstly, let's compare SAR with optical satellites. Optical satellites are passive in that, just like any normal camera, they gather reflected visible light from the sun to form an image. This light is at all kinds of wavelengths, and just like any other camera, they don't take images at night or through cloud very well. SAR, on the other hand, is an active sensor. It emits its own light source in the microwave portion of the spectrum, and these pulses travel to the Earth at the speed of light, and some are reflected back and gathered by the sensor. For any given sensor, this light is always at the same wavelength, and sensors that do this are labelled coherent, just like lasers, LiDAR, and ultrasound. For active sensors, we can be very particular about the wavelength we choose when we design the satellite. And the wavelength varies from satellite to satellite based on the main application of the data. Another key difference is the SAR is the imaging geometry. Optical satellites can sense the ground from any direction, vertically, down, or from an angle. SAR satellites, on the other hand, must look from the side. Unlike an optical camera, a SAR emits pulses and forms images based on the travel time of these pulses. To illustrate this, on the left we see a SAR looking straight down. Points A and B are equal in distance from the SAR and therefore return to the SAR at the same time. Echoes that arrive back simultaneously cannot be distinguished from one another, and they end up superimposed in the resulting image. So instead, we look from the side, and now points on the ground for the most part will be spaced at different distances from the satellite, at least when the ground is flat. Complications arise when there is topography, like mountains or open pit mines, and we'll talk more about that later. One last point regarding differences between SAR and optical data. Here are two images of the same erupting volcano. On the left, optical imagery shows the smoke plume obscuring the crater, and the smoke plume also casts a dark shadow on the image. On the right, a false color SAR image shows the whole crater with no smoke and no shadow. Neither image is objectively better, they are just different and both have their applications. We're now going to look at the way SAR orbits. This animation shows a pair of Sentinel-1 satellites orbiting opposite each other. Focusing for now on either one of those, the satellite is flying around the Earth, completing a lap every 100 minutes or so. Meanwhile, underneath, the Earth is rotating once a day. So over the course of a few days, almost all of the Earth is covered. Notice that the SAR has the opportunity to image areas whilst flying north. These are called ascending passes. And also, perhaps a few days later, it will see the same area whilst flying south. These are called descending passes. Recall that SAR satellites look to the side, so they could be looking left or right, but the convention for most is to always look to the right. So ascending passes acquire data looking east, and descending passes look west. Also note that SARs are sun synchronous. This means that they are aligned with our own definition of a day, as defined by the sun's apparent movement. And they revisit sites after some fixed number of days. For Sentinel-1, for instance, this is 6 days, and when I say 6 days, I mean to within a few seconds. Let's look now and compare some optical and SAR imagery of a mine. This is an optical image of the mine site. And this, as indicated by the graphic on the right, is an ascending pass of SAR data. So the sensor is looking diagonally down and east, and flicking back and forth will show you that these are indeed the same area. Slopes that face the sensor are very bright, and slopes facing away are darker. Intuitively, one might assume that brighter is better, but recall why satellites don't look straight down. Too many echoes return at similar times, and information gets mixed up. This is true also of these slopes. They return a lot of simultaneous signal, but most of it is useless. So it turns out that the darker slopes are the best ones using this ascending configuration for monitoring. Lots of the pulses are scattered away from the sensor, but the surface roughness ensures that enough data returns to the satellite to form its image. TerraSAR-X can acquire the same image every 11 days viewed from the same position. On a completely different 11-day cycle, the satellite will at some point happen to visit the same area whilst descending. Now it can acquire images of the area looking to the west, and as you might expect, the opposite slopes are bright or dark respectively. Collecting both sets of images provides the best coverage of the site, and we'll talk more about that in future lectures. We're now going to discuss some basics of the SAR signal. The SAR signal is emitted in discrete pulses of microwave light, which, just like any other electromagnetic light source, can be considered a wave. The height of the wave is the amplitude, or the brightness, of the reflected pulse, which, unlike the figure here, can vary a lot. And when we plot the amplitude values, we see something like the previous slides and the image shown here in the bottom right. Light and dark areas based on the angle of the terrain. Whilst there are all kinds of applications for amplitude data, it's not actually used directly for InSAR processing, so I'm not going to mention it too much after this point. The wave also has a fixed wavelength. During these lectures, I may at times use the Greek letter lambda to refer to wavelength, which is a standard convention. So lambda is fixed and must remain so to qualify as a coherent light source and for InSAR to work. Once a sensor is chosen for monitoring, switching sensors will typically mean starting from scratch, because you can't usually combine images from different sensors because of their different wavelengths. Note that frequency and wavelength are inherently linked and related by the simple equation lambda equals the speed of light over frequency. For InSAR, the most important aspect of this wave is the phase. Phase is an angular measure of distance along the wave. In the top right, you can see how angle can be used to express distance. When I'm halfway around the circle, I'm also halfway along the wave, or at 180 degrees. Phase and distance are related by a simple equation as shown, where distance in, say, centimeters equals phase times lambda, also in centimeters, over 2 pi. So how is phase used? Envisage a SAR emitting a pulse which travels as a wave down to the Earth and is reflected back to the satellite. These waves are only a few centimeters long, so there are many millions of them along the round trip to the Earth and back. When the pulse gets back to the satellite, there is some non-integer fractional wave left over, and it's the length of this fractional wave that is recorded as my phase value for some given pixel, nothing else. We have no knowledge of the many millions of waves that occurred along the pulse's journey, just the final fractional segment. So it stands to reason that for any pixel, the phase value will be between 0 and 360 degrees. Each pixel in the image receives a phase value, and when plotted, it looks like the image in the bottom left, completely random. It turns out, however, that this apparent noise is highly correlated over time, and when a second image is acquired and one image is subtracted from the other, the randomness disappears. This is at the heart of what InSAR is, differencing phase images, and the subject of future lectures. Just for reference, here is a map of the electromagnetic spectrum. Visible light is shown and has wavelengths on the order of nanometers, which are billionths of a meter. Microwaves are much larger and are in the centimeter range, and if we zoom in, we can see the microwave bands mentioned earlier, X on the short end and L on the long end. S-band is shown here for completeness, but right now there are no S-band commercial satellites. So why not just use one wavelength? Well, the shorter wavelengths offer higher sensitivity to displacement, but as a trade-off, they also offer higher sensitivity to unwanted effects from things like the atmosphere and from vegetation. So if you're monitoring in a vegetated area, you are forced to opt for a longer wavelength sensor to get any results at all, because shorter wavelengths are scattered unpredictably. Let's also revisit our SAR satellite chart and talk more about sensitivity to displacement, which is synonymous with measurement precision. As I mentioned, the available precision for displacement measurements is first and foremost a function of the wavelength. For standard InSAR, X-band data at 3 centimeters has an available precision of 1 or 2 millimeters. This ignores several other factors that could affect precision, but assuming they are negligible, this is the ultimate physical limitation on precision. C-band is nearly twice the wavelength of X, so precision is lower at around 3 to 5 millimeters. And L-band precision is around 2 centimeters because wavelengths tend to be around 8 times bigger than X at around 24 centimeters. So why is precision a function of wavelength? I talked about the neighbor playing music next door. The low frequency bass sounds are able to penetrate through the wall, but most of the high frequency detail is lost. Similarly with SAR, longer wavelengths offer coarser bass sound type measurements, able to penetrate vegetation, reflect and return to the satellite. Here we see the 3 microwave bands and their respective wavelengths, not to any absolute scale, but proportionally to scale with each other. Consider first the wavelength as my measuring stick. For X-band, that stick is about 3 centimeters long. But what actually matters though is the half wavelength. This is because the signal travels from the satellite to the Earth and back again. So I'm actually double counting the distance I'm interested in, and at some point I have to divide by 2. So using the half wavelength, my actual measuring stick is 1.5 centimeters for X-band. And on my measuring stick, regardless of how long it is, I have the same finite set of graduations. So 10 graduations for X-band and 10 graduations for L-band. The shorter the wavelength, the closer together the graduations. And if I misread the ruler, it's a smaller error than if the stick were longer. This is equivalent to higher precision for X-band. Alternatively put, we could say that regardless of wavelength, I have 15% of electronic noise to deal with. 15% of my 12 centimeter L-band ruler is nearly 2 centimeters, but for X-band, 15% of 1.5 centimeters is only 2.3 millimeters.